Okay, so this first one here, I want to know what the pH is, but before we talk about what the pH is, can you tell me about what the pH is before you do anything with your calculator? Can you look at that and say about what it's going to be?
Have to be, yeah,
So that would be 5, right? If it was just that part, but then it's 5, and then I add a little bit more acid. So then, what's the pH?
well,
Lower, but
not 4.
not less than 4. It's got to be somewhere between 4 and 5. Has to be less than 5. Has to be more than 4. Okay. So then, if I punch this into the calculator, what do we get? 2.59 e negative 5 equals, and log. So I get a pH equal to 4.6. So then what's my POH? 9.4. Those two things need to add up to 14. And so then what's my hydroxide ion concentration?
Negative, I mean, 10 exponent negative 9.4.
Excellent. So then the other way that I could write this would be just 10 to the negative 4.6. And either way you write those, they're exactly the same number. So whatever you feel more comfortable with.
The pH is just
Negative log of whatever that hydroxide or hydrogen ion concentration is, or hydronium ion concentration. So I've got this 2.36. So then I can say that my hydrogen ion concentration here, that's going to be 10 to the negative 2.36. Or you can plug it into the calculator and get a number, and it'll be something times 10 to the negative third. So make this add up to 14, and my POH will be 11.64. And so then my hydroxide ion concentration is going to be 10 to the negative 11.64. And again, you can plug that into the calculator and it'll give you some number times 10 to the negative 12 if you wanted a whole number exponent. Okay. All right, so we've got, you said change it a lot. It's too small. All right. So this next one, I want to know what the pH of this hydrochloric acid solution is if it's 0.2 molar. So what's important about the fact that we know it's hydrochloric acid?
It's strong.
It's a strong acid. So what does that do for us?
You don't have to figure out constant.
I don't have to look at any equilibrium constant for sure. That 0.2 actually is telling us. So if I'm talking about hydrochloric acid and I say that its concentration in moles per liter is equal to 0.2 molar, my H plus ion concentration is also equal to what? 0.2. And my chloride ion concentration is also equal to 0.2. You guys remember what the brackets around stuff means, right? Moles per liter. Anytime you see brackets around stuff. So like these brackets here, here and here and here and there, all that is, you don't actually have to put the capital M if you don't want to. Okay, so then I'm just going to take negative log of 0.2. So I get a pH that's equal to 0.7. And so what's important about this sodium hydroxide?
It's a strong base.
It's a strong base. So this 0.2 means the same thing that it meant for the hydroxide. So if I take the negative log of this 0.2, I'm going to get the 0.7 again, but what is it this time? This is my POH. So then my pH is actually going to be what? 13.3? Okay. So just make sure that when you're taking the negative log, you understand that in this one right here, I was taking the negative log of the hydroxide, so it's not pH, it's the POH, and this one was the acid, so it's definitely pH. Okay. And these two I have bolded, the hydrazine and the nitrous acid. Why?
Because they're not strong.
They're not strong. Okay, so I'm gonna actually need to look up what its Ka is. Do that, fly down here. And what is it? Sorry, nitrous acid? Is that right?
Yep.
All right, so nitrous acids, this 5.62 times 10 to the minus fourth. Okay. So I have a Ka equals 5.62 times 10 to the minus fourth. All right, so this is going to be equal to x, and 0.2. So what's the x, 0.2? We okay with that? That's the chemical reaction. So if that's my chemical reaction, then my equilibrium is going to be, my K value is going to be reactants underneath the product, so H plus, and then NO2 minus, and then HNO2. So I know the nitrous acid concentration because it was given, and I know it breaks up into those two pieces, and I don't know what those two pieces concentrations are, but I know that when it breaks up I get one of each, so I know their concentrations are the same, so I get that X and X. And so if I do the algebra on that, I get X is equal to the square root of 5.62 times 10 to the minus fourth times 0.2. And so what is that? Square root 5.62e negative 4 times 0.2 close parentheses equals, and I get 0.0106, and then if I take the negative log of that, I get a pH equal to 2. So we're going to do the same thing for the next problem, except I'm going to have to look up hydrazine. So that's a weak base. And so 1.26 times 10 to the minus sixth. All right. Ka, this is Kb, is 1.26 times 10 to the minus sixth equals x and x, and then H2N, is it 4? Yeah. Actually, I can just erase that because that's 0.2 down there. So what I have is H2N4 in an equilibrium reaction, and I end up with H3N4 with a plus charge. Did I get that wrong? Yeah, you're right, I'm wrong. That makes more sense. N2H4. And so what ends up happening here is there's a water molecule. And so what do bases do? What did Arrhenius say bases do? What's Arrhenius say a base does? Increases OH minus concentration of the water, right? Well, there's no O's or H's in that N2H4, right? So the OH must have been generated from a water molecule. And what's Lewis say a base does? A base. Lewis. What's Lewis says a base does? So Arrhenius says it increases OH minus concentration in water. Bronson-Lowry says it accepts a proton, and Lewis says it donates electrons. And remember that the nitrogen looks like this, right? And these two that lone pair of electrons there is the two electrons that donate. So the top of the nitrogens are going to be donating electrons for, in this case, a hydrogen. So these two electrons that are right here on one of these nitrogens are going to donate electrons for one of the H's on the water molecule. And so one of these H's is going to come over here and attach itself right there. And then what I'm going to end up with is an N3H4 with a plus charge on it and a hydroxide because the water molecule just busted apart. All right, and so then if I do the algebra on this one, I get x is equal to the square root of 1.26 times 10 to the negative 6 times 0.2. X is equal to 0.0005, negative log of that. Probably should put that in there. And I get a pOH equal to 3.3, so then I get a pH equal to 11.7. Does that look good? Which is stronger, hydrocyanic or acetic? How do I know that? So the only way to know that is to pop over here to this, and I've got, let's shrink this down a little bit. So my hydrocyanic is here at the bottom, and it's hydrocyanic is here, and it's 10 to the negative 10th, and my acetic acid is 10 to the negative 5th. So the hydrocyanic is actually 10,000 times weaker than the acetic acid is. So this guy has a 10 to the minus 10 Ka, and this one has a Ka of 10 to the minus 5th. So acetic is much stronger. And when we say strength, what do we mean by that? More dangerous? That's it. It's just the amount of dissociation. So when I say that the acetic acid is stronger, all I'm saying is that the acetic acid will separate, the H will pop off the acetic acid 10,000 times easier than it's going to pop off the HCN, the hydrocyanic acid. All right, so what's the resulting pH if I toss this into water? Okay, so initially, if it's just pure water, the pH is going to be 7, but now I'm going to throw 30 milliliters of this dilute hydrochloric acid in and see what happens. So how do I calculate pH? What do I need to know? pH is the negative log of what? H plus ion concentration in moles per liter. So that's what I need. I need the hydrogen ion concentration. So I need moles per liter of this stuff. So do I use this number here? The 0.15? No. Why not? I need to put this thing, I'm putting this into the water, so I need to know how much because the concentration is going to drop, right? I have 0.15 and I got 30 milliliters, and I'm adding it to 600 milliliters of water, so it got really diluted down. So my concentration is going to drop a lot. So you could do it a couple ways. You could just do a dilution equation, which is totally fine. So I can do 0.15 molar times 30 milliliters equals X times 600 milliliters. And then my new concentration,
So it's 600 and not.
I'm sorry, I'm totally wrong. It's 630. It's absolutely 630. My bad. So 600 and, no, it's 0.15 times 30 divided by 630. And so I got a concentration of 0.0071 molar. And so then if I take the negative log of 0.0071, I get 2.1, maybe 2.2. 2.2. So is that a big change in pH? Pure water was 7 and this drops to about 2, so that's 10,000 times more acidic. What was this equivalent to when we were looking at like common stuff? Do we remember where that was? What was on that level? Aspirin? That wasn't on our little list. Like gastric juices, Coca-Cola, tomatoes.
Oh, that was. It's like soda.
This would be a little more acidic than soda. Soda was around 2.5. So yeah, so about Coke, something like that. Okay.